All right, today we're going to tackle inverse and inverse trig functions. And if you look at Minnie and Mickey there, it's kind of like we're taking a vacation to Disney World. Kind of, because it's going to be that much fun. All right, inverse and inverse trig functions. So have you ever done anything that you wish you could take back or undo? Don't answer out loud. Right? We all have. Like, I wish I would have gotten then Coach Sluppick to tackle me. He was another guy in the math department. He was like 58 years old. He was kind of frail. He would have been, in hindsight, a better person to try to tackle me. It probably wouldn't have been as motivating to some or had as many hits on YouTube, but I'd feel better today, years later. So, yeah, I wish I could undo that. Well, with functions, there is a way sometimes, okay? There is a way to undo something if you have a function. If you plug a number into the function natural log of x, let's say, and you get an output, and you're like, oh, crud, I didn't mean to plug it in. How do I get back my original input? All you have to do is take that output, plug it into the function e to the x, and you get your original output back, okay? So a function that we say is one-to-one will have an inverse function that undoes its work that is also a function, okay? A function that is one-to-one. What does it mean for a function to be one-to-one? To be a function, for every x value, you can have no more than one y value. But you can have multiple y values that are the same coming from different x values. To be one-to-one, it means that for every x, there can be only one y, and for every y, there can be only one x. So it's kind of like a faithful monogamous relationship. For every one of you, there's only one of me, and vice versa. And that's why I have Minnie and Mickey there. They are a one-to-one couple, okay? Mickey is the only one for Minnie, and Minnie is the only one for Mickey, okay? They are a one-to-one couple. So a function that is one-to-one has to pass not only the vertical line test, but also the horizontal line test, okay? So if you were like trying to code a message and you were using the function, let's call it f of x, if you were using the function x squared as a primitive cipher, okay, you might take all the letters in the alphabet and square them and then transcribe them. If you plugged in like a 3 and you got an output of a 9, right? F of 3 would equal 9. The person on the other end would say, okay, if I know you squared a number to get 9, I can now decode your 9 and get back your original 3 by simply taking the square root of 9 and getting 3, right? But is there another number that you could code and make it into a 9? A negative 3, right? F of negative 3 is also 9. So when the person's trying to decode it now, there's a problem. If they're decoding it, it could have been a 3 or a negative 3, and now that's not a very unique cipher. So that's not a one-to-one function. A one-to-one function would be something that can code one way and be decoded in only one way. That's a one-to-one function. If you have a one-to-one function, then we say that it is invertible. So what is an invertible function? It's a function that is one-to-one, a function that passes the horizontal line test, a function whose inverse that undoes its work is also a function. We say that function is invertible. We're going to be looking today at invertible functions and how to find the derivatives of those inverses of those functions. Okay, so step one, the first thing we're going to do is review inverse functions. How do we find them? This is one way to denote a function, by a collection of ordered pairs. Okay, and we know it's a function because you don't have any of the x's repeated. 2, 3, negative 1, 4. That makes it a function. What makes it a one-to-one function? None of the y values repeat. Good. 5, 6, 2, 7. So they're all unique. So how would you find the inverse? Well, this function takes a 2 and turns it into a 5. So the inverse function, which we don't write with a highlighter, we denote like that. We read that as f inverse. Yeah, we read that as f inverse. It's related to f. It's not the derivative. It's negative 1. That means inverse. So the inverse function would then take out the 5, or take the 5 and send it back to the 2. If the function takes the 3 and turns it into the 6, the inverse function now takes the 6 and returns it to the 3. So what are we essentially doing with the ordered pairs? We're flipping them, right? Or transposing them, interchanging them, whatever you want to call it. Oops, I was talking and I did not do those right. Okay, if I was chewing gum at the same time, I would be falling down. Apparently I can't do more than one thing at a time. There we go. Yeah, and so notice, once you invert the ordered pairs, 5, 6, 2, 7 are now the inputs, and they don't repeat, so you know that the inverse is a function. But you could have told that in the beginning by looking to see if the y value is repeated. So that's how you flip an inverse, or that's how you find the inverse of a function if it's given as ordered pairs. How do you find the inverse of a function if it's given as an equation? Yeah, you do the same thing. You swap x and y, but this time you're doing the letters x and y, and then you're resolving for y. Now, how do you know that this is going to have an inverse that is a function without actually finding it? What's that? It's just yeah, you can identify it. Oh, that's just a linear function. A line, of course, passes the vertical and the horizontal line test. Here's another way to do it. If you replace f of x with y, remember, to be a function, we talked about this in pre-cal, to be a function, the exponent on the y can't be greater than 1. Because typically, the exponent on the y tells you how many y values you have per x value. So if that were y squared, it wouldn't be a function of x. It would be something we'd have to differentiate implicitly. There could be 2 y values for every x. So by the same token, if you look at the largest exponent on the x, that tells you how many x values there are for every y value. So really, to be a one-to-one function in the equation, your exponents on your variables cannot exceed 1 on either the x or the y. They could be less than 1, like a half, like a square root, but they can't be greater than 1. All right, so the way that we're going to find the inverse of this one is to interchange the x and y. And I like to use green for this because it is the money step. Interchange x and y. That's what we did in the ordered pairs. That's what we're going to do here for all x and y. And now the easiest way to do it is to resolve for y. You get x plus 8 equals 5y. And if you divide through by 5, it's the same as multiplying everything through by a fifth. So I'm going to call it 1/5 x plus 8/5. So notice the inverse of f is another line, which now we recognize for sure as a function. So now at the end, we'll just kind of give it that name, f inverse of x. So there you go. Now I want you to notice something. The y-intercepts aren't really related, are they? -8 and 8/5. That's kind of like, I don't know. They both have some kind of 8 in it. Maybe that's enough. But look at the slopes. Are the slopes related somehow? Yeah, one of them is 5 and the other one's 1/5. How are 5 and 1/5 related? They're reciprocals of each other. Is that a coincidence? Maybe, right? We only have one data point. We can't really make a claim, but we'll see. We'll keep that observation open as we see more data. We'll look to see if the inverses also have reciprocal slopes. Okay. Here is a graph of a function that is one-to-one. How do we know that one is one-to-one? Passes both the horizontal and vertical line test. Good. So to graph the inverse of this function, since I have given this graph the blue measles or the blue chicken pox, you can actually go through and invert all of those ordered pairs to get some data points. Let's see what that is. So this point on the far left is going to be -5, -3. If you take -5, -3 and switch it, you get -3, -5. So that's -3, -5. That's going to be right about there. The next point is -3, -2, which when you switch is -2, -3. That looks like it's right there. -1, 0 becomes 0, -1. That's right there. 1, 1. What happens when you flip 1, 1? You get 1, 1. Yeah, that was kind of funny. 3, 2. Flip 3, 2, and you get 2, 3. And then the last point here is, I don't know what it is, 4.5. Let's just call it 5, 4. How about that? Then we get 4, 5. And now if we connect those, it looks like that. That should be the graph of f inverse. Do y'all see any relation betwixt the blue graph and the red graph? Yeah. If you turn your head at a 45-degree angle, you'll see that there is a line of symmetry. And I'll put my meter stick there. course, if you're watching the video, you can't see the meter stick. So let's just draw that in there as a mustard yellow line. Mustard. All right, that's the line y equals x. And yes, if you remember from Algebra 2/Pre-Cal, to get the graph of an inverse, whether it's a function or not, to get the graph of an inverse, you reflect it across the line y equals x. Y equals x then becomes the magical mirror across which you reflect the graph. What is the inverse of y equals x? Yeah, you switch x and y, so you get x equals y, and you resolve for y, and you get y equals x. It is its own inverse, okay? So that's why it becomes the mirror. Now, y equals negative x is also its own inverse. Y equals 1 over x is also its own inverse, but they don't preserve the identity. Y equals x is the identity function. So it's the identity function, and it's its own inverse, and that's why it's the magic mirror. Okay, sweet. Let's look at something here. Over here, that the slopes of the inverses were what again? Related how? Reciprocals. All right. Let's take the slope of the tangent line. Let's use purple nurple here. Over here at -5, -3. The tangent line looks something like that. Ish. If you then draw the tangent line at its corresponding point, what do I mean by corresponding point? I mean the point that it reflects straight across, right? We took -5, -3, and flipped it to -3, -5. We call that corresponding points. That tangent line should look like that. Something like that. Do those tangent lines, first of all, do the tangent lines look to be inverses of each other? Yeah, if you were just to look at the two purple lines, they also appear to be reflections across the line y equals x. Does it appear that their slopes are also reciprocals of each other? Yeah, and we could prove that easily if we had the equations in much the same fashion that we did it right here. In fact, if you just replace this 5 with the letter m, m for slope, right, then down here you would end up with 1 over m. So it's going to be a fact, actually, that inverse functions are going to have reciprocal slopes. Now, if they are lines, their slopes are constants and the same everywhere. But we're talking about curves. That's why we're in calculus, okay? So their slopes are going to be reciprocals of each other, but they're going to be at the corresponding points, all right? So that's what we call those 2 points, corresponding points. So let's go back over to here. What are we going to call the point 2,5 and the point 5,2? Corresponding points. They're not the same point in general. We know they can be, right? Like 1, 1 corresponds to 1, 1. But in general, x, y on one function is going to correspond to yx on the other function. Those are corresponding points. So what we can say then is that inverse functions at corresponding points have slopes that are related how? Starts with R and rhymes with reciprocal. Reciprocal slopes. Good. All right. Let's go ahead and, well, I define it right here. We call the ordered pairs corresponding points. So on the function f, if there's a point called AB, if we let G be the inverse, sometimes we do that because f inverse is a little bit cumbersome. Sometimes we'll just define the inverse to be G of x. Then on function G, we have the corresponding point BA. Or another way to write it is if f and G are inverses, f of A equals B if and only if G of B equals A, right? Same thing? Yeah. Okay. So there's another way that we're going to be able to identify inverses. And it's this right here. It's kind of a nice little property. If you have a function and an inverse of that function, that is, it's invertible, they're both 1 to 1, then when you compose 2 inverse functions back to back, in either order, you're going to get the same thing you started with. Now, composition of functions is not always commutative, right? If you're offered $3 off and a 3% discount, what would save you more money? To take the $3 off first and then the 3% discount, or the 3% discount and then the $3 off? Take 3% off first and then $3 off. okay, because you're taking a percentage of a higher amount. So you're going to get more off. So the order in which we compose things, I should say, is not always going to be commutative. But there is one time where composition of functions is commutative, and it's when f and g are inverses, right? So if I start here at x and I take one step to the right and one step to the left, I'm back where I started, right? If I take one step to the left and one step to the right, the other way, I'm still back where I started. So if we start with x and I apply function g, it's going to take me somewhere. The inverse function f is going to then take that and take me right back to where I started, x. And it doesn't matter the order. If I start with x and apply f first, it's going to take me over here. Applying the g function takes me right back where I started. So not only are they commutative, f of g of x equals g of f of x, sorry, they're both equal to x every time. So it's the only time composition is commutative. So if you are ever given a question and it says, let f and g be two functions such that this holds true, you're going to be like, ah, f and g are related how? Third cousins twice removed? No, they're inverses of each other. Yeah, cool. So you know then that at corresponding points, their slopes are going to be related how? Reciprocals. Very, very good. All right, so let's go ahead and state this. There's three important bullet points that you need to understand when it comes to invertible functions. All right? Inverse functions, the first bullet point, at corresponding points have reciprocal slopes. Very important. Bullet point number one. Bullet point number two, inverse functions where have reciprocal slopes? At corresponding points. Very good. And bullet point number three, what type of functions have reciprocal slopes at corresponding points? Inverse functions. Yeah. They're all the same, but they're super duper important. We say this 3 times and you're like, I got it. And then we go forward a couple of weeks and I throw you a problem like this and you're like, I forgot. Okay. So inverse functions at corresponding points have reciprocal slopes. Here's how we say it mathematically. Let f and g be inverse functions of each other such that this holds true. F of g of x equals x, which equals g of f of x. That means they're inverses. With the following corresponding points, f of a equals b and g of b equals a. We can then say that g prime of b, remember b is the input on the function g, it's equal to 1 over f prime of a. Inverse functions, f and g, at corresponding inputs now, b and a, have reciprocal 1 over slopes. Now notice that this is not opposite reciprocal slopes. When do two things have opposite reciprocal slopes? When they're perpendicular to each other or orthogonal to each other, like the normal line and the tangent line. This is the same sign, just a straight reciprocal. All right? So if A is the input on F and B is the corresponding input on G, G prime of B is 1 over F prime of A, or similarly, you could say F prime of A is 1 over G prime of B. All right? At corresponding inputs, their derivatives are inverse or reciprocals of each other, because derivatives now interchangeable with the word slope. So inverse functions at corresponding inputs have reciprocal derivatives. Same thing, right? Mathematical synonyms. Okay, why is that important? Let's see. Example 2, okay? If f of x is equal to x cubed, remember, looks like this. It's your John Travolta Saturday Night Fever disco graph. Has a horizontal tangent right there at 0. It's 1 to 1. Hello, cool dude. Find the following. What's f of 2? 8. Nicely done. What's f prime of x? 3x squared. Nicely done. Sweet. What's f prime of 2? Well, these are easy questions. Can we test over this? 3, 2 squared, right? Which is equal to 12. 12. So what does that mean? That means that at 2, right here, we'll call this 2, right there, the slope of that tangent line is 12. The slope is 12. Now it says to find f inverse of x. Okay, so step 1, let's call f of x y. So now we have y equals x cubed. If we interchange x and y, remember that's the money step, cha-ching, we get x equals y cubed. And now we solve for y, and we get y equals the cube root of x, also known as x to the 1/3, right? And we know what that function looks like. Let's come up here and graph it. We'll graph it in red. That's the one that has a vertical tangent at the origin because the x cubed has a horizontal tangent. We know it's not differentiable at there at 0, even though it's smoothly connected. All right, now it says to find that. What the heck is that? That's f inverse prime. That's the derivative of f inverse. So if we come back over here and we label that now as f inverse, I'll leave it as x to the 1/3. I'll come over here. If f inverse is x to the 1/3, then f inverse prime. You could see why we sometimes just call f inverse or set it equal to g, because again, that's cumbersome notation right there. But I can take the derivative pretty easily. It's the power rule, 1/3 x to the negative 2/3. So if I clean that up, that's 1/3 cube root of x squared. Now it says, let's do something else that I didn't do here. Let's sneak in here, kind of call it E part 2. What is f inverse of 8? Well, plug it in right here. What's the cube root of 8? 2, right? So notice what I'm doing here. I'm taking f of 2 and getting 8 on x cubed, and I just found the inverse equation, and now f inverse of 8 is 2. So I'm just verifying that they're inverses of each other. But I actually have the inverse equation. So now, since I have now the derivative of the inverse equation, I could take the derivative of the inverse at its input 8. So f inverse prime of 8, if I plug it into there, I get 1/3. And remember, you probably want to take the cube root of 8 first instead of squaring it. The cube root of 8 is 2. 2 squared is 4. So I get 1/3 times 4, which is 1/12. Now notice part G says f inverse prime of 8 again. You know why? Because part F was supposed to just be f inverse of 8. That was a typo. I snuck that in there as E too. So what we essentially have here is the following. We have the function f, which at x equals 2 had a slope of what? 12. The corresponding input on the inverse function was 8. We just verified that. And what was the value of its derivative at 8? 1/12. Now part H says, what is the reciprocal of f prime of 2? Well, if f prime of 2 is 12, this would be 1/12. So what we're basically doing is we're verifying that that little formula that we just memorized works. Okay? So why would we need to memorize this? Why would we need to know that inverse functions at corresponding inputs have reciprocal derivatives when I can simply, if I needed the slope of the derivative, I could just find the inverse equation, take its derivative like I normally would, and then plug in its own input to get that number. Well, doing it up through part G did require me to be able to find the equation for f inverse, right? Do you think that's always possible? Ponder it while we pledge. To the flag of the United States of America, to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Honor the Texas flag and pledge allegiance to the Texas, one state, under God, one and indivisible. Look at example 3 during the moment of silence and think about if that one can be solved for x to be able to find the inverse equation. Can we solve that one for y? Once I switch x and y, can this one be solved for y? No. Okay. So that's why we need to know that little rule. You can't always find the equation of inverses.
You will not be allowed to leave with it until you have the cover on it. Also, the theater department is producing the odd couple.
Yay. We don't need to be able to find the equation of the inverse function to be able to find the slope of that graph at a point. All we need to know is what the corresponding point is. Okay? So this gives us kind of a backdoor approach, a sneaky way to get in to the inverse club without being able to find the equation of the inverse.
Also, the dual credit Applied Texas deadline for spring 2018 is tomorrow. If you plan on taking dual credit and are not currently a dual credit student or have not already done the Applied Texas, please see Ms. Garcia in the back office.
I'm going to go ahead and do example 3, competing with Ms. Shriver. Tonight is the homecoming candlelight pep rally right after the freshman game. Read part A.
Forms may be turned in starting Wednesday, October 18th, and must be received no later than the end of the school day on Wednesday, October the 25th. Also, Texas Tech will be here tomorrow at 10:30 a.m. Get your passes now in the College and Career Center. ASVAB scores are also in, and you can pick those up in the College and Career Center as well. Thank you.
All right. So, first of all, x to the 5th plus 2x minus 1. We just said you can't find the inverse. Is it even 1-to-1? Well, we know x to the 5th, it could look something like this. It can have up to 4 local maximums. That would definitely fail the horizontal line test. But this one does end up being 1-to-1. Here's how we know. We know it's a polynomial, so it's continuous for all x. If you take the derivative, you get 5x to the 4th plus 2. What do you know about 5x to the 4th plus 2 for any value of x? It's positive. It's going to be 2 at the very least, if not more, okay? So what does that mean? If a continuous function is monotonic increasing, guess what you could say about it? It's also 1, 2, 1. Now, it has to be continuous, because think about tangent of x. Tangent of x is monotonic increasing over its domain, but it fails the horizontal line test really badly. But it's not continuous for all x. It has vertical asymptotes. But a continuous function that is monotonic increasing or decreasing is going to be 1-to-1. So now, since I know I'm interested ultimately in the slope of the inverse at 2, and I can't find the inverse equation to find the derivative, all I got to do then is figure out the corresponding point. So here's a little clue. It says, what is f of 1? If you plug in a 1 to the original, you get 1 plus 2 is 3. 3 minus 1 is 2. So we know on the function f, there is a point called 1, 2, right? Which means on the inverse function, f inverse, there is a corresponding point called 2, 1. And look at this. If I'm trying to find the slope of the inverse at 2, we know it's just the reciprocal of the slope of f at 1. And that's easy for us to find. Watch. Here's f prime of x right there. What's f prime of 1? 7. All you have to do now is flip it, and you get 1/7. Boom! We didn't even need the equation of the inverse. All right, we'll pick up example 4 tomorrow. It'll make more sense. Have a great rest of the day. We'll see you at the Candlelight Pep Rally.